Yay!
Yay! Hey everyone, here's a slightly more complicated example of energy conservation, now involving a spring and a rough plane and height. So suppose we compress a mass on a spring. Remember, now, you might have seen already some classes do this now, some classes will wait. I'll probably show this a little bit later when we actually do springs. So just take it right now as a given that the potential energy of a spring is just 1/2 k delta x squared. So it's the amount that you compress the spring is delta x, so you square it. And then k is just a number. It just reflects how stiff the spring is. The greater the k, the stiffer the spring. Again, we'll do all this in more detail when we do springs and oscillating motion. But right now, it's just a number. Just take it to be a number. So this is just the amount of energy you can store in a spring. So that potential energy is, in some sense, the stored energy inside the spring, right? Because you can get it back out when you let the spring go. All right, so we're going to compress the spring by a certain amount. And then we're going to let it go. And then the mass is going to go across this horizontal region that doesn't have any friction. And then you're going to go up this plane. And this plane is going to have some friction. So what we're interested in is how high above the ground does the mass rise? And notice at this point, I mean, think about in terms of energy, what's going to happen? The total amount of energy we have available is going to be how much we compress the spring, right? That's the initial energy. So we're going to have an EI, the initial energy, and that's just going to be spring. There's no kinetic at first. It's on the ground, so there's no potential. And this is going to, and then the final energy, is, we have to be a little bit careful, right? The final energy, now, when it gets up there at the end, it comes to a stop, right? So you're tempted to say that the final energy is just going to be 0, which is true. There's no kinetic at the end. But look, it's gained some gravitational potential. It's gone up in height. So we have to be a little bit careful. The final energy is just going to be gravitational, U-gravitational, which is just mgh. We know how to do that. Okay, so if the energy were conserved, if the plane didn't have friction, we're sort of done. You would just set those two energies equal to each other and solve for h. The problem is that the plane does have friction. So what's the effect? Is that the friction takes the energy out of the system. So the difference between what I start out with and what I end up with must be what the friction took away. That's how I think about it. Okay, so let's put those things in and we can go ahead and solve. So the initial is the spring 1/2 k delta x squared minus the final energy is mgh. Work done by friction. Okay, we've done this before. This is just going to be the force of friction times the distance over which it works, over which the mass slides. So the force due to friction, here we go. We've done this before, mu times, it's on a plane, right? So it's mg cosine theta. That's our normal force. And the distance that it goes is just that distance up the plane. And this is, again, something we've done before. Just use your trig. I want to know that distance, that hypotenuse. So that must be h over sine theta. There we go. So that is our general equation. Now the physics is done at that point. Now it's just sort of algebra. So what we want to do, we want to solve for h, right? So 1/2 k delta x squared equals look, I can factor out. I'm bringing the mgh over to the right hand side, and then I'm going to factor out an mgh. That'll make things a little bit easier. mgh times, let's see, that would give me a 1 plus mu over tangent theta. Look at that. Because I've got cosine over sine, right? When tangent is sine over cosine. So it's just 1 over tangent theta. Okay, anyway, if you do the algebra, that's what you get. And I want to solve for, what the heck am I solving for? H. All right. So this means that my h Should be k delta x squared. Let's just get a general formula. K delta x squared over 2 mg times 1 plus mu over tangent theta. All right, because I think we know all this stuff. If you're given, let's put in some numbers. Let's just see what we get. What numbers did I use? What numbers did I use? Did I write them down? I don't even think I wrote them down. Let's see, suppose my K is 800. Delta X was, let's say, 50 centimeters, 0.5 meters. Just to make the point, I'll do 50 centimeters. Mass is 2. Let's see, mu is 0.5. Theta is 30 degrees. Right, okay, so we put all this stuff in, and what do we get? I put all these numbers in, and I got just some typical height, 2.7 meters. Okay, so here is the general result. And then when you put in some typical numbers, you'll get some answer that it's not crazy. You know, if I got like 2,700 meters, I might wonder if I've made a mistake. But that seems kind of like a reasonable thing. Okay, so here's how you would handle something involving friction and spring and something that involves a little bit of algebra to get the final answer. But still, it's just the setup is what you need to pay attention to. The setup back here, still involving these energy principles, turns out to be pretty easy. Once you get the initial energy and the final energy and any non-conservative energies like done by friction, once you put those into an equation, you just use algebra to solve for what you want. This is why energy conservation is such a powerful principle.